undetermined coefficients, the so-called annihilator approach, we start this section by introducing a most important concept in mathematics, and the concept is on the question of what is an operator. An operator in mathematics is any term that can be applied to a function, can be applied to a vector, can be applied to a space, where it changes fundamentally the makeup of that particular entity, whether it's a function or a space, a graph, a vector. So something that can be applied to a function that changes its makeup. There's several things that does that. One example is a derivative. Take the derivative of a function and it changes the makeup of that function. The integral is said to be an operator. Take the integral of a function and it changes the makeup of that function. Correct? Well, the terms don't look the same. You look at a function, look at its derivative, and you say, man, they're totally different. Well, they're supposed to be because there's an operator. And so the term operator is very similar to what you would consider a person or a thing to operate on something. It goes in and it takes out, it adds, it rearranges, and so you get something else. In linear algebra, a matrix system can be an operator. You can take a matrix and you can apply the matrix onto a vector and you get a different outcome. So you could say capital A times X, A is a coefficient matrix, times X, a vector, and you get some little b. You get some different terms for b. Change the matrix A on X and you get a different output. So a matrix can be also an operator. So there are several operators. The main two that you are accustomed to would be the derivative and then the so-called integral. But there are several operators in mathematics. We want to be able to solve a differential equation using this idea of a differential operator. We denote the operator, and maybe you've noticed my notation for all of my courses in calculus and up to now, is that I may write a capital D signifying a derivative, and it's just simply saying to you that capital D is a derivative operator or a differential operator. An example of the differential operator, if you take this differential equation, y double prime plus 4y prime plus 4y equal to 0, we just represent the derivatives with the so-called operator. So y double prime is d squared, and then y prime is d. And if there is no derivative, then we do not denote that position with anything. So this particular problem can be transferred into writing it as d squared plus 4d plus 4, which is said to be operating on y. So that's why it's parentheses d squared plus 4d plus 4, close parentheses. It looks like it's times y, but it's actually the operation on y equal to 0. And then you can simplify that as what they did there. Represent the following differential equation using differential operators. So you could write this as d squared plus 3d plus 2 said to be operated on y. That's equal to 4x squared. And you can simplify that if you wanted to. So this is d plus 1 times d plus 2 operated on y is equal to 4x squared. So we introduced the operator here so that we can talk about another type of operator. It's a differential operator. Here is said to be an annihilator. So here I want to wipe out a term. How can we eradicate, how can we remove a particular function by using a derivative? And just a very simple example of that is if I have a function y equal to, let's say, 2x. Well, I can wipe out 2x by taking its second derivative. The first derivative will give me 2. The second derivative will give me 0. So here, how can we annihilate a function by using a so-called derivative? Well, we have a schematic chart here that will show us the forms of these annihilators on certain functions. The so-called annihilator operator is denoted with this capital L. So how can I annihilate a function f of x? So to annihilate it, there should be some annihilator operator on to f of x that should give me 0. If a function is a constant function, like y equal to k, then just the first derivative will wipe it out. So the first derivative on the constant gives us 0. If the function is x, then the second derivative will wipe it out. So d squared wipes it out. So if we have functions of the type, if it's 1, x squared, x cubed, all the way to x to the n minus 1, then we say that the annihilator operator is d to the n that's going to get rid of it. So the so-called operator, the annihilator operator here, is always for the exponent one term further. So if I have x squared, I need d to the third power to wipe it out. That's all this guy's saying, right? So say, for example, here, if we have a function f of x is equal to 6x to the third, then d to the fourth is said to annihilate 6x to the third. So that's this whole idea of d to the n and x to the n minus 1. So you just do the next term further. Now we use this schematic chart for so-called polynomial terms. Polynomial terms. It changes for exponential terms. So it's a complete different formula for the schematic chart. And then if you have the transcendental functions or trigonometric functions like sine and cosine, then there's a whole different formula for that as well. Okay. So here, if I have functions that are said to be exponential, e to some alpha x, then the differential operator d minus alpha is the constant term up in the exponential part, d minus alpha to the nth power is said to annihilate any of these terms. Again, the nth power here for the annihilator represents the next term up, the plus 1 term. So these terms listed here for equation 5 or statement 5, they go up to the n minus 1. Let me give you an example. So say, for example, if f of x is equal to e to the 5x, then we say that, see, alpha would be 5, so d minus 5 is set to annihilate this e to the 5x. We get 0. Well, you can check it and see. So here, let's just call that y, if you will, is equal to e to the 5x. And so d is said to be 5 times e to the 5x. So indeed, this d minus 5 applied to e to the 5x can be written as this. This is d times e to the 5x minus 5 times e to the 5x. Just distribute the e to the 5x through the parentheses. So the differential operator on e to the 5x is 5 times e to the 5x. And that's minus 5 times e to the 5x. You get 0. Now watch this. What if you have y equals to x times e to the 2x? So here, this term for x is x to the first power. So what we say is that d minus 2 to the second power is said to annihilate x times e to the 2x. You see this d minus alpha to the nth? So that n compared to here, the x to the n minus 1. So here, this is x to the first power. And so this term here has to be the next term further, which will be to the second power. Okay? Now for sine and cosines, we use this very complicated formula. So if it's any combinations of e to the alpha of x times cosine beta x, x times e to the alpha of x times cosine beta x, x squared e to the alpha of x cosine beta x, all the way up to x to the n minus 1 e to the alpha of x cosine beta x. The same chart works out for sines as well, so we use this formula right here. Hopefully, the trigonometric form that we have would only involve cosine and sine. And if it's just cosine or if it's just sine, then all you use is d squared plus beta squared. Now, typically the problems that I've given you will not use number 7. I try to keep it as simple as I can using cosine beta x or sine beta x, and that can be annihilated by d squared plus beta squared. Okay. Well, let's look at some problems. Here is a theorem. And I will apply this theorem to some problems down below where we need to apply it. But let me say that suppose L sub 1 annihilates some function y sub 1. And then also suppose that L sub 2 is the annihilator for y sub 2. Then the way you would annihilate for the superposition principle, you want to annihilate c sub 1 times y sub 1 plus c sub 2 times y sub 2, it's going to be the product of the annihilators. So in the product, L sub 1 times L sub 2 will annihilate the sum of c sub 1 plus c sub 2. We don't need that here for these problems, but there are some problems down below where we need to know that fact, and I'll apply it then. So look at numbers 1 to 10. Write the given differential equation in the form L of y equal to g of x, where L is the linear differential operator with constant coefficients. So if possible, factor L. So sniff example here, if we take number 3, number 3 becomes d squared minus 4d minus 12 this is applied to y is equal to x minus 6. And if we could factor that, let's see, d minus 6 times d plus 2 applied to y is equal to x minus 6. Okay. So that's all you do there. What about number 5? Number 5 is d times d squared plus 10d plus 25 on y is equal to e to the x. Maybe we can factor one more time. You can write that as d times d plus 5 to be squared on y is equal to e to the x. So that's not bad. In problems 11 to 14, verify that the given differential operator will annihilate the indicated function. So take number 13. Here's what they're saying. If you look at this term here, this guy is annihilated by d minus alpha, d minus 2. And then this term here is annihilated by d minus alpha, where alpha is negative 5, so that becomes d plus 5. So this is a sum, right? This is e to the 2x plus 3 times e to the negative 5x. So the sum is said to be annihilated by the product of the differential operators. So that's why they have d minus 2 times d plus 5 annihilates the sum. And they are referring to this theorem up here, that if L sub 1 annihilates y sub 1, and if L sub 2 annihilates y sub 2, then the product L sub 1 times L sub 2, which you get close to El Segundo, but no, anyway. I never knew that El Segundo was a real city. You all probably didn't grow up, maybe some didn't grow up watching Sanford and Son, but he would always refer to a city named El Segundo. And I always thought it was just some made-up city. I got a letter in the mail from some wacko guy, but the city was El Segundo, California. I said, get out of here. This is Sanford and Son. Some guy trying to, I don't know where he had a house listed for sale, and this was a realtor saying he's a realtor, he can help you sell your house, and his address was El Segundo. I said, man, come on, I don't want no junkyard. You know. Anyway, Fred Sanford, but okay. Wrong crowd, wrong generation. They had an old Sanford and Son marathon on the TV over the weekend. Man, I got messed up watching that stuff. But anyway, so yeah, L sub 1, L sub 2, El Segundo. That's where it comes from. But so let's see. But anyway, even if you didn't know that particular theorem, we'd need it for the next set of problems below this, because they kind of give it to you. They say, does this product, will this guy annihilate this? Well, let's see. Now, here's what I'm going to do. I'm going to take this product, I'm going to simplify it. So if you simplify it, that's d squared plus 3d minus 10. I'm going to apply that to y. And we want to get 0. Well, that's the question. Does it actually give us 0? Well, I need the first derivative. So the first derivative would give me 2 times e to the 2x minus 15 e to the negative 5x. D squared, or the second derivative, is 4e to the 2x plus 75e to the negative 5x. So based on this information right here, this is the second derivative on y, plus 3 times the first derivative on y minus 10 times y. Does that give us 0? Well, we're going to check and see. So the second derivative on y is this term right here. So this is 4e to the 2x plus 75e to the negative 5x plus 3 times the first derivative. So 3 times this information right here. 3 times 2 times e to the 2x minus 15 times e to the negative 5x minus 15 times minus 10 times y, excuse me. Times y, and y is e to the 2x plus 3 times e to the negative 5x. So we simplify all of this. So this is 4e 2x plus 75e to the negative 5x plus 6 times e to the 2x minus 45e to the negative 5x minus 10 times e to the 2x minus 30 times e to the negative 5x. All right, so let's see. So I have 4 e to the 2x plus 6 e to the 2x. That gives me a 10 e to the 2x, which would cancel out with this guy, right? And then 75 times e to the negative 5x minus, this is minus 45 and minus 30, so that's minus 75 e to the negative 5x. It cancels out with that. So that does indeed equal to 0. So the product, actually you see that the product of the annihilators will annihilate the sum of the functions. That is that L sub 1 times L sub 2 will annihilate y sub 1 plus y sub 2. That's important to remember that, because you would kind of want to think that L sub 1 plus L sub 2 ought to annihilate y sub 1 plus y sub 2, but it does not. Okay? There's a proof of that in the book. I've bypassed that because I want to try to get to these problems. So I do not require that proof for the test. Problems 15 to 26, find a linear operator, differential operator that will annihilate the given function. So look at number 15. Oh, I don't want red. So 1 is annihilated by just the first derivative, right? And the second derivative will annihilate the 6x. And then the fourth derivative will annihilate the negative 2x to the third. So the answer, and I got a right answer here, that the differential operator that will annihilate all three at the same time would be d to the fourth. See that? The fourth derivative will annihilate the first derivative, will annihilate the constant 1. It will also annihilate the 6x, and it will also annihilate at the same time the negative 2 times x to the third power. So the answer here, all you need there is just d to the fourth. It does everything. Now look at 17. So d will annihilate the 1, we get 0. And then d minus 2 would annihilate that 7e to the 2x. That'll give us 0. So what will annihilate 1 plus 7 times e to the 2x? Yes, sir. Yes, sir. So the answer here is d times d minus 2. Does everybody see that? Because the product of the annihilators annihilates the sum, right? This is the sum 1 plus 7 times e to the 2x, right? D will annihilate the 1, and then the d minus 2 annihilates the 7 e to the 2x. So d times, parentheses, d minus 2 gets rid of the whole thing. And that's what this theorem is saying right here. You see, for number 17, this would be d. So else at 1 would be d. It will annihilate the 1, right? And then d minus 2 will annihilate the 7 e to the 2x. Then the product, right, d times d minus 2 annihilates the sum of 1 plus 7 times e to the 2x. All right. What about 19? Can you do that one? What do you get for that? That's all you need. One, the 6x and the 2x to the third, they're all in that same schematic scheme of a polynomial, right? Right. Number 17, 1 and e to the 2x, they're in two different spectrums, right? One is a constant, e to the 2x is exponential. Right? And even if you wanted to do the product for number 17, you just have too much stuff there. Right? Think about it. If you did the product, that'll be d times d squared times d to the 4th. So that'll be what, d to the 7th, the 7th derivative. But it would have won out at the 4th derivative. Right? You would have gotten 0. We'll just stop at d to the 4th. How many derivatives does it take to get that function to go out, to be wiped out to 0? That's all they're saying. So what do you get for 19? You see that formula for if it's cosine, it's like cosine beta x, or if it's sine beta x, it's just one simple formula, right? Did you get it? So it'll be d squared plus 4, right? Because beta is 2. So it's d squared plus beta squared. D squared plus beta squared. So for 19, cosine 2x, beta is equal to 2. So to annihilate this guy, you need d squared it's said to be d squared plus beta squared. So here, this is d squared plus 4 is your answer. You see that guy? Let's see, where's the term? I think it was here. If it's just cosine beta x, or if it's just sine beta x, all you need is d squared plus beta squared. And that gets rid of the cosine or the sine, especially if they're by themselves, right? Okay, good. Now, here's where we want to try to conclude this section by solving the same differential equation that you had in section 4.4, the same one. We're going to cover 3 methods in this chapter of solving a non-homogeneous differential equation. The first method was the superposition approach. And it was the superposition approach, and the main header was undetermined coefficients. That was section 4.4. Now 4.5 is the method of undetermined coefficients, but here using the so-called annihilator approach. They're very similar, and that's the really cool thing about it. It's like you're not almost doing anything different, but this method is supposed to be a little bit smoother, right? So it doesn't take long to work it out. Let's take number 35. Look, the problem that I will give you on the test will look something like 35, 37, 39, 40 or 41. Believe you me, these guys are not as hard as the ones where you kind of compound like the sines and cosines and all the other stuff in there. So I keep this very straightforward. That does not mean that I'm trying to avoid giving you problems that you may see later on. You will see some very crazy problems in engineering science and other forms of courses of mathematics. The next section is the variations of parameters method. And that method, that's where we kind of say, I'm going to use this forever. Because that's like the granddaddy of solving these non-homogeneous differential equations. And so for that particular method, it doesn't matter how complicated the problems may look, we can apply that. The methods for undetermined coefficients is good, but they're still elementary, because if the problem gets more complicated, then these methods, you can be sitting there kind of all day trying to figure out what's A, what's B, what's C, and that kind of stuff. So, the variation parameters method, even though it's long, it is set in a standard way. I do this first step, second step, third step, fourth step, always the same. Doesn't matter. So, take you some time to kind of get the process, but once you get it, man, it's straightforward and it's easy. So let's look at 35. Y double prime minus 9y is equal to 54. We're going to solve the differential equation by the so-called undetermined coefficients here by using the so-called annihilator approach. So here's the first thing we're going to do. First thing you're going to do is just go ahead and solve, like you did in the previous method, the homogeneous differential equation. So we solve y double prime minus 9y equal to 0. So this implies that we have m squared minus 9 equal to 0. That implies that m is equal to plus or minus 3. So y sub c is c sub 1 times e to the 3x plus c sub 2 times e to the negative 3x. Step number 2. What we're going to do for step number 2 is this. Let me write it out. We're going to write y double prime minus 9y equal to 54 using differential operators So if you think about it, notice that d squared minus 9 times the y represents the y double prime minus 9y. Now look at here, this would be g of x. Look at g of x, it's 54. What will annihilate 54? You said D? Yes. Yeah. D. Okay. So if that be the case, then I'm going to say now D times D squared minus 9 applied to Y gives me 0. Annihilates the whole thing. So from here, I'm going to write the solution using the given operators. So that means that here I get D equal to 0, and I get D is equal to 3, and I have D is equal to negative 3. And probably better notation is little m for the auxiliary. So m is equal to 0, m is equal to 3, and m is equal to negative 3. So I get y is equal to, this is c sub 1 plus c sub 2 times e to the 3x plus c sub 3 times e to the negative 3x, which the 0, the 3, and the negative 3 came from this differential operator, d times, basically d minus 3 times d plus 3. Right? So I get, ideally, it's like d equal to 0, but it's not d. We've transferred this to the auxiliary equation, so m equal to 0, m equal to 3, m equal to negative 3. Now this is said to be the solution in the generic sense, because notice that for the complementary solution, we had e to the 3x, e to the negative 3x, which I get those guys right there. So where is the c sub 1 coming from? It's coming from the solution for the non-homogeneous part, right? That 54. Yeah, right, so good. So now what we do here is we say, let y sub p, it's going to represent this term, just say let y sub p equal to a. Y prime is 0, y double prime is 0. Go back to the original equation. I'm going to plug in, let me write the original equation over here. This is y double prime minus 9y equal to 54. So I'm going to plug in that information. So here, y is equal to a, y prime 0, y double prime 0. So this is 0 minus 9 times a is equal to 54. Excuse me, a negative 6. So this negative 6 just replaces the c sub 1. So my solution is y is equal to, you can write it in the beginning or at the end, it doesn't matter. If you write it at the end, we just change these coefficient subscripts. C sub 1 times e to the 3x plus c sub 2 times e to the negative 3x minus 6. Now let me work one more and then I'll be done. Just should take no more than about 4 minutes to work the next one. I want to make sure that you definitely get it. Let me do 39 because 37 kind of looks like 35, right? So let's do something a little bit different. Let's look at 39. That's right. Plus. So y double prime plus 4y prime plus 4y equal to 2x plus 6. So the first part, we solve m squared plus 4m plus 4. That gives us m plus 2 times m plus 2 equal to 0. So we get y sub c is c sub 1 times e to the negative 2x plus c sub 2 times x times e to the negative 2x. Now, look at g of x, which is 2x plus 6. What differential operator annihilates 2x plus 6? Okay, d squared. So d squared annihilates 2x plus 6. So we have here d squared times d squared plus 4d plus 4 annihilates the whole differential equation. So, that is to say, this is d squared times d plus 2 times d plus 2 equal to 0. Step 2. So this implies that we have y is equal to, let's see if you see this, c sub 1 plus c sub 2 times x plus c sub 3 times e to the negative 2x plus c sub 4 times x times e to the negative 2x. Do you see how we get the c sub 1 and the c sub 2x? That's on the repeat of that d squared, right? How do you represent if you have m squared times m plus 1 equal to 0? You get m equal to 0, m equal to 0, m equals to negative 1. How would you write the solution for this guy? You say y sub c is equal to c sub 1, right? Because that's basically c sub 1 times e to the 0x, right? Which is just c sub 1. And then it'll be, since the zeros are repeating, it'll be plus c sub 2 times x times e to the 0x. So this guy would be c sub 2 times x plus c sub 3 times e to the negative x. This is just something on this side. It has nothing to do with that problem, but it does in an indirect sense, right? In terms of how did I get the c sub 1 plus c sub 2 times x? It came from that d squared, right? Think about that as being m squared, m minus m. M equal to 0, m equal to 0 again. So it's a repeat, right, of the constant terms. So notice here that for the complementary solution, you got this term and you got that term. Well, that's that guy, and that's that guy right there, right? So that means that the c sub 1 plus 2, c sub 2 times x would represent the particular solution for that 2x plus 6. So here, what we do is based on how this guy is written. We say let y sub p equals to ax plus b. So then you go right back to section 4.4. So then y prime is equal to a, y double prime is equal to, oh mercy, what is that? is all of this? Okay, I lost my work. I don't know where it is. Huh? What's going on? Okay. I don't like that, but okay. So y prime is a, y double prime is 0. So you go back to the original problem. So y double prime, 0, plus 4 times y prime, that's 4 times a, plus 4 times y, and y is said to be ax plus b, and that's equal to 2x plus 6. So we get 4a plus 4ax plus 4b is equal to 2x plus 6. Let's get the coefficient for x, which would be 4a is equal to 2. And then 4a plus 4b is equal to 6. So a is equal to a half. If a is a half, this is 4 times a half plus 4b equal to 6. So that's 2 from the 6. We get 4b equals to 4. That implies that b is equal to 1. So y sub p is 1/2 x plus 1. So the solution would be c sub 1 times e to the negative 2x plus c sub 2 times x times e to the negative 2x plus 1/2 x plus 1. And that's it. Thank you.